Okay. Everyone can see my screen now? Okay. Awesome. Yeah, for some reason, I'm not able to get my laptop to show the presentation slides properly because I wanted to use my laptop that way I could draw and not have to use my mouse. I think I'm gonna try one other approach. That way, I don't have to draw using my mouse so that you guys can actually like understand or not have to like interpret my handwriting kind of thing. Let's see. Okay, I'll try this. Okay, if this doesn't work, I'll just go ahead and get started. Before I get things started in chat, does anyone, if you could just type in the problem, like which problems you want me to go over, like say like whether or not it's a frequency response or the op amp problem set, and then say like which question it is. I think I have all the questions in this presentation slide. So if you guys want to go like start with this particular problem, maybe one of like the harder ones or something, that's fine with me. Okay. Let me... Okay, do you guys see my notepad? Um, like side by side with the presentation. Should be showing. Okay. Let's see chat. I see one yes. So okay. All right. Okay, so the problem that we're gonna start with is from Sebastian. So the op amp to be fall 2023. So let's go to that one first. Op amp to be that's is that this question, Sebastian? No, not this one. To be the ordering's kind of weird. Do you know what problem number it was? Is it this one? Is this one? Okay, got it. All right. I'm gonna zoom in on this. Okay, so let's start off. Let's read the problem. So for the following circuit, we're assuming VA, which is our input voltage, is 1.5 volts. We have an RA of 10 kilo ohms, R2 and R3 are the same values. Okay. And does it tell us what I think I said right? RA, R2 doesn't say what R1 is. So I assume we're gonna find R1. Okay. So when you guys approach an op amp problem, there are a handful of things you need to take into account. One, what type of op amp circuit are we dealing with? Is it one of the common ones that we are familiar with, like the inverting, non-inverting? Is it a differentiator? Is it summing? Or is it a more complex circuit? Another aspect that you need to keep in mind with these problems is, are you dealing with the ideal version of the op amp or a non-ideal version of the op amp? And the problem should say specifically, like it will tell you oh, this is a non-ideal op amp. Or if it doesn't, it's kind of implied because they might give you like the open loop gain, for example, or like a particular characteristic which would signify the op amp is not ideal, right? So oftentimes that's one thing you need to keep in mind with these type of problems is what type of op amp configuration are we dealing with, as well as what kind of assumptions are we allowed to make with this particular circuit. So we have a VA equal to 1.5 volts, RA is 10 kilo ohms, R2, R3, 6 kilo ohms. Okay. So we want to find R1 such that Vx, which is our output, is equal to negative 2.5 volts. And we're assuming an ideal op amp. So this is great. So what does ideal op amp mean? Well, we can say that Vp is equal to Vn, and we can assume that the current going in to the terminals is zero, right? These are the properties of an ideal op amp. Super important that you remember this. If it was not ideal, we would then have to, we know our output equation or V out is equal to this gain parameter, which is this is the closed loop gain multiplied by the voltage at the positive terminal, voltage at the negative terminal. You'd use this equation, and then you have to systematically find each of these, like what VP, VN, and what your gain is. So just something to keep in mind. You want to memorize these equations. But we're dealing with the ideal case, so we're going to look at that top equation. So any other characteristics, so assuming the ideal is op amp, and we are saying that VB is 1 volt, VC is equal to 3 volts. It says for the following questions, assume R1 is 48 kilo ohms and VB is equal to VC equal to 0. Okay, so that's for the next set of, it's kind of weirdly placed. Okay, so I think this, and yeah, anyone, like I said, anyone feel free to hop in chat to say something. I think this is for the other problems. It's kind of like oddly placed, unfortunately. But okay, so this first part, find, we're looking for the resistor R1. That's this guy. And we have a parameter for output voltage. We know all the following inputs voltages. And if we notice, we have three inputs here. 1, 2, and 3. So this is kind of an annoying circuit to solve if you were to do it with all the inputs um like connected at once. So something we can take advantage of to solve these kind of problems where you have multiple inputs is you can take advantage of superposition. And all superposition lets us do is this allows us to deal with each um, part of our circuit by turning off sources. If it's a current source, you set the current to zero. If it's a voltage source, you set the voltage to zero. And then solving each of the aspects of the circuit individually with all the sources off but one, and then adding up the result of each of them. So that's one way we can solve these kinds of problems. Or you can just try and solve it directly as well. So I think in this case, I'll try and solve it directly just to kind of see um, like what that kind of solution looks like, I guess, the long way. And we'll go from there. So we have 1.5 volts. I'm going to actually write in the values now. So 1.5 volts for this. We have RA is equal to 10 kilo ohms. This is going to the positive terminal of this op amp. And we said what R3 is a 6K. Okay. VB is 1 volt. And over here, this is also 6K. This is 3 volts actually. And then finally, R1 is what we're looking for. And this is negative 2.5 volts. Okay. So this is an ideal op amp. So this point on, let me change the colors. Okay. So this point and this point on the op amp are the same. And if we look carefully, we also know that there's no current flowing into the positive terminal and the minus terminal. So the voltage at this point is actually going to just be 1.5 volts directly. And that's going to be the same voltage at this node. So I can redraw this circuit with that in mind without the op amp. Draw something like this, where we have this Vx, we have 3 volts down here, 1 volt down here, and then this is 1.5 volts. And this just becomes a 214 circuit problem, right? It's pretty straightforward. 6K is a 6K. Um, right. To find this resistor value, we know that this resistance is going to be Vx minus this node here. I'll call this Vn, divided by the current that's flowing there. So we can find the current in this branch. And to do that, well, we know the current in the other branches because we have all the voltages. So we can very easily start, say, with this branch, and we can find this current. Let's call this current I1. And then on this branch here, and by the way, Vn is, can anyone tell me what Vn is going to be? Actually, I want to see if folks are paying attention. 1.5 volts. Okay, perfect. Kind of easy to see there. So we'll find the current flowing in through both branches. So we'll find I1. I1, if we assume, um, let's make the convention so the higher voltage, so that current is flowing from top to bottom, from like high voltage to low voltage. So we do 1.5 minus 1 volt divided by the resistance. This is 6 kilo ohms. And then we have, so that current's flowing in this direction. And then we have this current over here. We're going to say current's flowing from high to low. So I'll call this I1. We'll say I2 is 3 minus 1.5 divided by 6K. And this current is flowing up. This current over here is flowing down. Right. So can anyone on their calculator really quickly tell me what I1 and I2 is going to be? Or if you can do quick mental math as well, I'll take that. Anybody? Anybody? Okay, I1 is okay. 0.83 micro. Okay. And then I2. Okay. So I2 getting 0.25. I think 0.25 milli is the correct one. Let's, I guess, scale them both to micro amps. Okay. All right. So I3 is the current flowing through R1, our resistor of interest. Can anyone tell me what the correct equation, assuming we're saying the direction of current is flowing down in the resistor? Can anyone tell me what the equation is between I1 and I2? Is it adding? Is it subtracting? Let's see if folks have their 214 knowledge. So just as a refresher, maybe I'll redraw it here. Okay, I1, someone's correcting. I1, it's saying it's 83 micro. Let me double check on my side. I think 83 micro is correct. Yeah, 83 micro is the correct value for I1. Okay. So I assumed I1 was flowing this way. I said I2 is flowing this way. And now I'm saying I3 is going to flow down. Assume R1 is there. Can anyone tell me what the correct equation is for I3? So when we're thinking about currents flowing into a node, right? I3, yes. Benjamin, yes, you have it correct. So one way to think about it is, generally speaking, if you can, I drew it this way just to like show you guys how you can break down these problems. Generally speaking, I would have like chosen all the currents to go in a particular direction, maybe all flowing into the node or all flowing out. Uh, but I wanted to spice things up a little bit. In this case, yes, I3 is going to be plus I1 minus I2, right? Because I1 is flowing in the same direction as I3. I2 is flowing the opposite direction, so you're going to have to flip it. It's going to be a negative sign. So yeah, Benjamin's equation there is correct. So simply, when you subtract this 83 micro from the 250, you're going to get negative 167 microamps. Like so. And now R1 simply just becomes in the, according to our voltage convention here, or like our sign convention that we've done, will be something like this divided by, okay. And can anyone tell me the final answer? I'm getting like roughly like 21 kilograms. Someone said 24. Are we? 24. Okay. Did I make a mistake? Maybe I made a mistake. All right. Yeah, I did. I did. Yes, 24. 24 kilograms. Okay. There you go. So the key takeaways, like in terms of how you set up these problems, right? First and foremost, is it ideal or is it not ideal? Right. The first part of the problem told us right away it's not ideal, or it is ideal. From there, taking a look at the circuit, how it's configured is very important. You can see what tricks you can take advantage of from 214. Those skills should be very sharp, right? In this case, we could very quickly see that, um, VP and V minus, VP and VN are going to be equal to each other, and the current's not going to be flowing. So we redraw the circuit, and then it just becomes a 214 problem, right? So the faster you can analyze these problems, the quicker you'll be during the exam. So let's go on to part B. So we want to find Vx, and for the remaining parts of the problems, we're going to assume R1 is 48 kilo ohms, and VB and VC are equal to 0. So that should make our life a little easier. We're just going to ground those two inputs. All right, so VB, we want to find Vx now. So Vx is in question. If the op amp has an offset voltage of 15 millivolts, but we're assuming an ideal op amp otherwise. Okay. All right. So same approach. We're going to redraw the circuit. Okay. So these voltages are this is just ground. R2 and R3 were 6 kilo ohms, like so. And now this is actually these are parallel. These are connected in parallel, so we can actually combine these resistors to a single resistor. Can anyone tell me real quick what the value is going to be? So it's super easy.
Uh, 3K,
The parallel combination of two 6 kilo ohm resistors.
3K.
I'm looking for 3 kilo ohms, 3 kilo ohms, right? So for folks who had that in their head but maybe didn't say it, just keep that in mind, right? Two 6 kilo ohm resistors, like two resistors of the same value in parallel become half. In case um maybe that wasn't clear. If the two resistors are the same value and they're in parallel, you just half the resistance. That's what's going to be. Okay. This is now 48 kilo ohms. All right. The difference with this problem is now we have an input offset voltage. So our offset voltage, the way we model it, if you guys remember in lab, the whole idea of the offset voltage is that these the VP and V minus, the internal um like the way they model this device, something like this, where you have this internal resistance which is huge, like you want it to be a really large value, that way VP, that way there's like very little current flowing in. But on top of that, um there is a slight offset voltage mismatch which appears on the op amp. And often the way we model it in problems is that it's going to be something like this, like VP is equal to V offset plus VN, right? Where naturally we like to assume in an ideal case that the voltage on the positive terminal, the voltage on the negative terminal are exactly equal, but that's not true. In reality, there's always going to be some slight offset, and that's often we model that by adding the offset voltage in this way. Is this familiar to anyone in like class? Like, has he gone over this concept? Okay, I'm seeing a yes. Okay, great. So often, how that's a couple of ways, it can be modeled a couple of ways. Sometimes I've seen it like some people would just throw in a like a voltage source here, for example, like a DC voltage, something like this, and call this V off. Right. But now we can solve the problem the exact same way. And the problem tells us we can assume the op amp is ideal otherwise. Uh, that's a good question. It can go both ways. In this case, I think, hmm, I'm pretty sure it's defined by the actual sign. Like whether or not the offset is positive or negative. That's where you know which side is like to place the voltage source. So if there's a positive offset, if I'm not mistaken, I think you have to add it to VP, if I'm not mistaken. But that's a good question. Is there a specific reason the DC source was put on the minus terminal of the op amp? So in this case, because the offset is positive, it's a positive offset. I'm pretty sure. I want to make sure. I want to be confident in this. I might have to. Oh, whoops! Did I just lose my screen share? Oops, sorry guys. lost that. Okay, there we go. Okay. Okay. Now my screen share doesn't want to work. Okay. But did I answer Zanir and Ben your guys' questions? Does that like make sense in terms of like the offset voltage while I'm trying to fix this? Yes. Okay. Okay, that's good. All right. I think I got it back. Yeah, I don't know what's going on. All right. Okay, so yeah, to solve for, yeah, we'll just continue to solve the problem normally. Um, it says assume everything else is ideal. So we now throw in this offset into our um equation here, but we can assume that the current flowing into the positive terminal and the current flowing into the negative terminal is going to be zero. We still can take advantage of that. So now I'll take a look and we'll say that VP, which is equal to VA, which was previously was 1.5 volts. I think it stays the same too, and this is 10K. There we go. So VP is going to be 1.5 volts. It's going to be offsetted by the voltage offset slightly. Where did the 0.7 volts on the DC source come from? I'm not quite understanding your question. 0.7 volts? Oh, sorry. Did I put 0.7? I meant to put 15 millivolts. I don't know why I put 0.7. Yeah, sorry about that. Okay. All right, so VN is going to be 1.5 plus or sorry, subtracted by the offset. So 1.5 minus 15 millivolts. This will be I think 1.485 volts. And then from here, solving the rest of the circuit becomes straightforward. The circuit just becomes a voltage divider if you think about it, um, because we have our output, we have this resistor, this 48 kilo ohm resistor on the feedback, and then we have this 3 kilo ohm resistor. And remember, current doesn't flow into the negative terminal because we defined it up here, but we do know this voltage now, right? This is our VN, right? So to find VX, this becomes a kind of a straightforward process. Can anyone tell me what Vx is going to be equal to? For example, like we know the voltage divider, if we were looking for Vn, we would say Vx, Vn is going to be equal to Vx times 3 kilo ohms divided by the sum of the two resistors, right? So in this case, we're looking for Vx, so we're just going to move this over. Why did I make so why did I make VP equal to 1.485? Oh, Vn. Oh, because there's an offset voltage, right? meaning the positive terminal and negative terminals are not exactly equal. The voltage drop between them are not going to be exactly the same. So the negative terminal gets shifted slightly because of the offset that they define in this problem. In this case, it's 15 millivolts. So, and the 1.5 volts comes from the source, right? It comes from VA. And then, okay, so Ben, you got Vx is equal to 1.58. Can anyone else confirm that? This should be 1.4.85, roughly 51K. I think it should be, the voltage should be higher than that, right? This is, there we go. Okay. Yeah. Yeah, I'm getting 25.25. Answer sheet gives 25.75. So that means if the answer sheet's giving that, then that means that the offset, I probably have this equation slightly wrong. I think the offset needs to go on the other side. Probably needs to be like this. Whichever way the what's it called? The way the note sheet specifies it, that's going to be the convention that we want the offset to be. Let me double check this real fast just to make sure. 1 divided by 3. Yeah, okay. So just to clarify, I made a little mistake. So the offset voltage, since it's positive, the equation's actually going to be Vn is equal to Vp plus V offset. It's like this, right? So Vn is actually going to be, this is actually going to be a plus sign here. Instead of 1.485, this will be 1.515 volts, like so. If we propagate that all the way through, the correct answer will match the solution. There we go. So yeah, just to note the convention. So it seems when V offset is positive, and I think that makes sense too because our positive terminal, right? If we assume there's an internal resistance, or sorry, there's an internal source here. If this source is positive, then it's going to be leaning towards the positive terminal. So I think that convention is correct, like this. So if it's positive, and then if it's a negative offset, for example, I think it would be like this. But generally speaking, I think it should be placed like this. But double check your note sheet for these kind of problems. But the general procedure for these problems are super straightforward. Once again, is this an ideal case? Is it not? But and then systematically breaking down the equations of the circuit, that way it works for you, is very important. And turning it into a 214 problem rather than a 325 problem will make it a lot easier for you. So because here we just get a basic voltage divider circuit, we take advantage of the fact those resistors are in parallel, so we just combine them to be 3 kilo ohms, and then from there the solution becomes very straightforward, and we see the voltage here is going to be 25 volts. Now, one thing to note, 25 volts is not very practical for an output voltage. Remember that op amps have rail voltages, and in lab, we see rail voltages of +5 and -5 volts, though we can go all the way up to 15. So, um, and I think you guys will see problems like that where you have a rail voltage and you will start to clip. So this voltage output might actually clip because of this large gain provided by that 48 kilo ohm resistor. Right. So, okay, any questions about this part. I know the V offset thing might have been a bit um like confusing because I switched signs, but hopefully like the idea makes sense. We're just adding a voltage on top of the VP and VN. Like they're not equal to each other if there's offset voltage, right? There's going to be a slight deviation in them. Just that knowing which way it is important in this case. If it's positive, it'll be like this. Any questions? Okay. All right, I'm going to move on. All right, so part C, it says find the closed loop transfer function. Okay. Vx with respect to x over Va over s, assuming an op amp with a unity gain bandwidth equal to 5 megahertz. Okay. An open loop gain of 112 dB. And then hence sketch the Bode plot of the transfer function. Okay. All right. So, couple of things. The unity gain bandwidth and the open loop gain. These are very important characteristics. And these, mind you, these parameters here define and immediately tell us that this is a non-ideal case, right? So we no longer can assume VP is equal to VN, and we no longer can just say I plus, or sorry, IP, which is equal, or they're not equal to each other, but maybe let me not write it like this, but we can't just assume the current flowing in is zero. Let me just say it like this, right? And on top of that, whenever you're given the open loop gain and the unity gain bandwidth, we have to think to the um, uh, op amp, like the open loop gain response of like frequency response of an op amp, where you have this DC gain, right, which is our A0. You have this dominant pole here, and often there's a second pole that we'll see often, but sometimes we don't include it. Sometimes you do if it's a first order response we care about. And then you have this bandwidth here associated, usually called FT. Um, and this is a this is like the base characterization of the op amp, like the pure um frequency response. And oftentimes we are just operating on a portion of this curve whenever we're using the op amp. And you know, the higher gain that you want, the lower your bandwidth, right? So if we wanted a really high gain, we have a shorter window to operate frequency wise, right? Versus say if we're operating at a lower gain. So this graph is just explains and characterizes how well your op amp performs given a particular bandwidth or given a particular gain that you're looking for. Okay. So the problem is asking us to find the closed loop gain. The closed loop gain is the gain when the op amp is in a particular circuit configuration. So in this case, we have this circuit configuration. Okay. So there's a couple of ways we can do this. We can take advantage of, I think there's a shortcut. It's been a while since I've done this, so please forgive me. There's the open loop transfer function that we can derive, and then there's the closed loop transfer function. Now, we can derive the closed loop transfer function from scratch by analyzing the circuit, but if I'm not mistaken, there is a shortcut that uses the open loop transfer function. Um, but I don't remember the equation. I have to go through the notes, but I'm pretty sure there is a fast track to getting the closed loop transfer function. But before we do that, let's set up the open loop transfer function. So the open loop transfer function is of the form, I believe it's AV, which is equal to, no. I believe it's something like this. Yeah, it's this. And then we're gonna need a couple of parameters here. So I wrote down somewhere some key equations for these type of problems that you guys will need to memorize. Whoops, maybe it's higher up. Nope, it's not here. Give me 1 second. Let me find this page with my equations on it. Yeah. All right. Okay. So I've got my equations. So one key equation um that's super helpful. It's like a couple set of equations that are pretty helpful here in characterizing the op amp is these equations. So this all these equations are in the notes, and you should try and like have a strong understanding of like what these equations mean and what your like what the takeaway is. For example, this first equation is the gain bandwidth, and it's equal to the closed loop gain times the frequency of the bandwidth. And then the next one here, this is the uh what's it called? This is the operating frequency of like a particular point in the op amp that you're operating at. F of t, this is, I mean, I defined this earlier up here. This is the frequency of like the open loop, like cutoff frequency basically. And it's divided by 1 plus the open loop gain. Now, sometimes you're able to simplify this to be the unity gain bandwidth divided by the closed loop gain, and then so on and so forth. So to start, one approach that I'm gonna take, I'm looking at this, I'm like, let's see. I think what I'm gonna do, I'm going to derive the transfer function from scratch, the closed loop transfer function, and kind of show you guys like what that approach is, how you do it, and then fill in the gaps from there. So I'm redrawing the circuit, like so. And I'm gonna label everything. R3, R2, R1. And we assume this is ground. Great. And we already learned from earlier that these resistors are 6K. So I'm just going to combine this to be one resistor and call it 3K. And this is 48 kilo ohms. All right. So because the op amp is no longer considered ideal, in order to find Vx, we know Vx is going to be equal to the closed loop gain, or sorry, this gain equation times Vp minus Vn. And this is going to be the open loop gain divided by 1 plus S over omega B. So we need to find what Vp and Vn are because we no longer can say this. This is no longer true. So we need to define them separately. Okay. So Vn Vn is actually pretty easy to find. Uh, by the way, we still assume that the voltage, we can assume the current going in is like really small, for close to zero. So Vp is just going to be 1.5 volts, but Vn is now actually going to be equal to this voltage divider circuit here. So it's actually going to be a product of Vx. It's going to be Vx 3 kilo ohms over 48 kilo ohms plus 3 kilo ohms. Any questions on how I jumped to this step? Hopefully this was pretty clear. Okay. From here, we're going to plug everything in. So we're going to say Vx A0, 1 plus this. And then we have Vp, which we know is 1.5 volts. Vn, which is Vx 3 kilo ohms over 48 kilo ohms plus 3 kilo ohms. Okay. Our open loop gain was given to us as 112 dB. We're going to have to convert this from dB to volts per volt. So this will be 112 divided by 20, and we'll do 10 of this. Can anyone plug this into the calculator real fast? Tell me what it's going to be. 40,000, 400, 400,000 volts per volts. Okay. Yeah. Okay. And then to find WB, which is just 2 pi of this, I'm going to look at our equations here and see what we can take advantage of. So, I think we're going to use this equation because we know the unity gain bandwidth is 5 megahertz. And then G of V, this is actually the ideal gain, assuming the op amp is ideal. So the gain of the op amp um, in the ideal case is we can just derive the transfer function assuming Vp was equal to Vn in this case with everything grounded, of course. So in that configuration, I think it just simply just becomes what we say 3K. I'm going to call that Rx, for example. Rx, Rf plus Rx, something like this. That's why Vx equals Vn. So our transfer function just becomes something like this. or our gain, sorry. Yeah, I think that's correct. And I'm pretty sure this is the same as this. Um, or am I thinking about this wrong? Oh yeah. So sorry. The gain is output over input, so Vx over Vn. Okay. I was like I knew I had this mixed up. There we go. So yeah, it's gonna simplify to this. It's gonna be an inverting or non-inverting um configuration. That's what it is. So yeah, you guys should kind of see that this is gonna be equal to that. This is GV, if I'm not mistaken. So we know what RF is. This is 48K. This is 3K. So the gain just becomes 17. So F of B is going to be our unity gain bandwidth divided by GV. So 5 megahertz divided by 17. This is going to be equal to 294 kilohertz, like so. Okay. All right. So, um, and sorry, I need to have this in terms of VA, like this. There we go. Okay. All right. So we're on the home stretch. We just need to plug everything in, move things around algebraically, and then we'll have our transfer function. Okay. So if I factor this across, move everything that's Vx to the other side, then I can solve for Vx over Va, which would be our um, end solution that we're looking for. Okay. So first I'm going to factor everything. So we're going to get VO, VA, 1 plus S over this minus X, say 3K, 51K. Okay. 3 over 51 is not a nice number. Okay. So I'll just leave it. Okay. And then solving for this, we should get. Okay. So this should be the form of the final answer. We'll just have to plug in all of our values here. Let me pull up the answer sheet here just to make sure we're on the right track. All right, so now let's simplify this and let's plug things in. I'm going to multiply. Let me see. What's going to be the best approach here? Okay, I'm going to multiply the top and bottom of this by 1 over SB A naught, like so. Something like this. So that should give us a 1 at the top. And then at the bottom, we're just going to get 3 over 51 here. And then this should just be this. Something like this. Okay. And now if we simplify, we know this is 2 pi FB. We found FB previously to be 400K, just about. A0 was, wait, was FB? No, FB was 294 kilohertz. 294 kilohertz. This was 400,000. Okay. Okay, let me pull my calculator. So on the denominator here, I should get 1 over A0 plus S. So it's going to be super small values here. 1 over 200, 400,000. Okay. Okay. So now I just need to get this in the right same form as the final answer. So we're looking for a form like this. Uh, it's not A0. Okay, 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 I got it. Okay. So, okay, so at this step right here, okay, I had the right answer. I'm just confusing myself there. Okay. So you're gonna get S over WB. You're gonna get this 1 plus A over 0. This is gonna be like super tiny. Plus this 3 over 51 term right here. That should give you I think this is this, right? Yeah. Yeah. Okay, so here I got so I got 1.8 uh e to the 6 for this. And then for here, I got 0 point. No, 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 this isn't right. This isn't right. This isn't right. Oops. Oops. Okay. Yeah, I got 7e to the 11 here. There we go. And then for this, I get 0.058, like so. And if we do 1 over this is actually going to be um about 17. And we want this portion of the equation to be 1, so we'll factor out uh we'll factor out the like 0 point like this number, right? And which will be 17, which is like the same as multiplying everything by 17. So we'll multiply the top and bottom by 17, like so, and then you should get 17. It's like 16.99999 repeating, but you should get, oh, what's that? Strange pages. You should get this, and then 7e to the 11. Uh, divided by 17 is getting like 4.4, 4.3 e to the 10. I need to double check this portion, but I'm getting 1 plus all of this. Is this PowerPoint posted somewhere? I've looked around. No, this is not posted. I just made this PowerPoint earlier today. Um, but the PowerPoint really won't be helpful. The notes, I guess these notes here would be what's more helpful. So I'll have to come back to I'll go ahead and send you guys the presentation. Okay. Uh oh, did someone give me the wrong value for this? Okay, maybe I don't have the right. It looks like this omega b value. This should be omega b. So this is going to be, we're expecting this to be 1.85 megahertz roughly. So um maybe there was a mistake somewhere. Hold on. I think that, yeah, that's 2 pi fb, right? Pi times 300. Yeah, that's correct. Okay. So your A0 is going to cancel out on the denominator here. Um, just keep that in mind. But this is going to be the final answer for the closed loop transfer function. Yeah, as you can see, this can get a little messy, so you really want to take time to practice this. But just to summarize like the process and the procedure to tackling this, first and foremost, recognizing that this is a non-ideal case for the op amp. So you can't assume, you have to make these assumptions. You can't assume that the VP and VN are going to be equal to each other. That's important. Also, you have to have these equations memorized, right? Understanding that um, when the op amp isn't ideal, the output voltage is equal to the gain of the op amp times VP minus VN. And this AV term is going to be this, right? It's going to be the open loop gain divided by 1 plus SW over B, right? And that's characterized by this graph right here, right? So really make sure you have these equations in your head, that you understand them, and how they're useful. Once we got to this step, deriving the output equation, right? Finding the VP, finding VN. VP is just equal to VA. Very straightforward. The VN is the voltage divider portion. So that's all this right here. And from there, simplifying, it's a ton of algebra. So take advantage of your calculator. I think there's an algebraic mistake here somewhere, but the process is correct. As you go down, you'll need to find this FB term because you need to know what this is, right? And that's where I recommend like at least maybe screenshotting or going through the lecture notes, these equations right here. Oh, Kent asked, how do we know it was non-ideal? So the reason we know it's non-ideal is because it's asking us to find the closed loop transfer function given the unity gain bandwidth and the open loop gain, right? You only ever use the open loop gain and the unity uh, UGBW, unity gain bandwidth, if the op amp is non-ideal. Because remember, if it was an ideal op amp, the closed loop transfer function is just going to be like the non-inverting equation, right? The 1 plus RF over RA equation, V out over VN, right? So that's how we're gonna know like this is the ideal transfer function for the op amp. But in a non-ideal case, we know that the gain is going to change as a function of frequency because of the non-idealities of the op amp. That's what the unity gain bandwidth characterizes. So because of that, whenever they give you the open loop gain and the UGBW, you know that this is going to be a non-ideal case. I no longer can just say this is equal to this, and this equation up here is not going to be valid for you, right? You're in the lecture notes. He should. There's a portion of the lecture slides which highlight this specifically, and they call this the open loop transfer function, the one up here. There's a way to find the closed loop transfer function from the open loop transfer function super quickly. So if you guys go down and go through the notes and memorize that portion and look over it, that should be helpful for you. But if you don't remember it, during the exam, you have to know how to break down the problem to get to the answer, right? So, and that's, you know, by doing that circuit analysis, that's going to be how you find it. Okay, looks like some more questions. Is there a similar way to find it? Um, is there a similar way? I assume you're saying simpler. Is there a simpler way to find it? That's it's gonna be in the lecture slides on how to use the open loop gain to find the closed loop gain. Pretty sure there's a portion. I skimmed over the lecture slide notes, but I'm pretty sure I saw a section there. Exam closed note. I believe yes. I believe it's closed note. Um, can we find the closed loop gain and then use the unity gain to find the frequency? To find like your cutoff frequency? Yes, that's what this equation is. Yeah, I think I'm understanding your question. Uh, but this is if you wanted to find the frequency, um, yeah, you're basically finding the bandwidth that your op amp is operating at given the operating conditions. But yes, yeah, Donovan, I think, or Aiden, sorry, I think I'm understanding your question. Okay. Um, all right, you guys good if I move on to another problem? Can I talk about closed loop and open loop again? Okay, sure. Okay, so open loop versus closed loop. Okay. So so the major difference between open loop and the closed loop characterization of the op amp. One way to think about it is when you have an op amp device not connected to anything, right? There is the manufacturers have characterized the op amp using a Bode plot when it's not connected to anything. And that open loop response looks like this. You guys should have seen something like this in lecture, where I mean your x-axis is frequency, it's a Bode plot, right? And you have like dB, this is your gain. Where up here, this portion is your what we call the A0, which is your open loop gain, right? Open loop gain. And this is usually a huge number, right? It's like 200,000 volts per volt. Huge, 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 huge. When we're talking about op amps, all this graph is telling us is that, okay, the higher the frequency and it's just comparing the gain versus frequency and the relationship that we're seeing. So if you're building a device and you want a gain of say 20 volts per volt, right? You would go to the portion of the graph that's 20 volts per volt, and then you'd see this response. You're going to draw a flat line all the way up to the open loop response. And just to make it a little more clear, let's give it a different color. Let's call this graph red here. And then we'll continue from the open loop graph like this, right? The width, the frequency width of this portion of the graph is your bandwidth, right? This is your bandwidth at 20 volts per volt when you're operating at that condition. Now, if you were operating at a much higher gain, say like say 2000 volt per volt, your available frequencies to operate shrinks dramatically. So the open loop characteristics of the op amp just characterize, and it just helps understand, okay, when the op amp is not connected to anything, how does it respond? How do we characterize the gain versus frequency? And that's what this graph is, right? The moment you jump to a closed loop condition, you're choosing a point on this curve to operate at, right? And the closed loop meaning you have resistors, you have say like an RF and R1, and you've characterized the closed loop gain. So for this, if we assumed it's an ideal case, we know that the output, right, this is an inverting circuit, is just going to be this, right? And this is some gain that, the circuit is operating at, right? Say the magnitude of it was say like 30 volts per volt or something, right? Say it's negative 30, but it's 30 volts per volt. That tells us which portion of what available frequencies are there um, for us, like, for this circuit to operate at. So the open loop characteristics, often this is given as a graph, or it's given as some parameters as A0, which is the open loop gain, the unity gain bandwidth, and the unity gain bandwidth, very simply, is bandwidth. So you can break it down. So unity gain, this is where the gain is equal to 1. And then the bandwidth is the available frequencies, like the frequency range, right? So unity gain bandwidth is just, okay, when the gain, so when we're looking on this graph here, when the gain is equal to 1, what is the bandwidth? That's all that means, right? What is the bandwidth? And a gain of 1, by the way, is 0 dB. So that's when this graph is at 0 dB, right? So that's effectively the entire range, the maximum operating bandwidth of the device. That's what the unity gain bandwidth means, right? Um, I'm missing some other ones. But there's some other, yeah, there's like FT, for example. There's FB. Um, FT is the like the frequency at this particular point on the curve. FB is the first pole, is the dominant pole. Sometimes it breaks it up as F1, F2, sometimes as the two poles of this graph. But the lecture notes explain decently like what the open loop characteristics mean. Um, Let me see. So open loop means it can be anywhere on that curve, but closed loop is at a certain point. Exactly. Yeah, closed loop is at a particular point. You have resistors connected to your circuit. You have to solve what the gain is for the particular circuit, and you're going to be operating at a particular point on this curve. So you're bounded by your closed loop characteristics for a particular op amp. So that's why in the problems, like if you see a graph or if you see, oh, the gain bandwidth product and the open loop gain is X or is are these values, that should tell you that, okay, it's like someone has given you a device and is giving you a spec sheet and saying, hey, we're going to operate at a particular point on this op amp. What is going to be the characteristics if we operate at that point? So that's the reason why you can't assume it's ideal, because this graph is literally characterized by the manufacturers of the op amp. So it literally describes physically how it operates, how well it operates at different frequencies and different gains. So that's the whole reason why whenever you see a graph with your open loop characteristics or you get an open loop gain or unity gain bandwidth, unless the particular problem doesn't say, hey, assuming an ideal op amp, like right here where it says ideal op amp, right? Ideal op amp, right? Here, just as assuming an op amp with these parameters, oh, we know right away, okay, this particular portion of the problem, this is going to be a non-ideal case. Is that clear? Yes? Okay, great. Okay, let's see. I want to try and move a little faster here. We got 30 minutes. Any particular problem anyone wants me to jump on? I think there was another problem someone mentioned way early on. Frequency response, exam one, problem one. Okay, that was the so Ben, I think Ben was asking for this problem. Ben, do you still want me to work through this problem? I don't know if he's in here. Is he here? Okay, I don't think he's here. Okay. Does anyone want me to go through a different problem? If not, I'm more than willing to go through this problem. I wanted to go through like a harder frequency response problem. I felt this was not too bad, but I don't mind going over it. Just like really quickly, am I gonna post my notes? I'm gonna try. I'm using a Remarkable, so hopefully the PDF is like normal. So we're gonna find out. But I'm gonna try. I'm gonna try to post my notes for sure. Um, okay, op amp spring 2023 exam one problem 2A. Okay. Okay, Kyle, I'm gonna try and find that one. Um, problem 2A. Nope, that's Kyle, can you tell me which one it is exactly? Is it this one? No, no, we just did this one. Yeah, we just did this one. Oh, is it this one? No, it's not this one. Ah, it's this one. There we go. Okay. All right, let's zoom in here. Okay. All right, let's get right into it. So design a single pole. This is important. Okay, single pole, low pass filter. Using the circuit shown below to meet the following specs. So we have a cutoff frequency of 2 kilohertz. We have an input resistance of 3 kilo ohms. We have a gain of 40 dB in the passband. Okay. So let's quickly draw this bode plot. I think that's even one of the requirements. Sketch a magnitude bode plot to show the resulting magnitude frequency. So we're going to skip to part D, actually. So we want a low pass filter. So the low pass filter looks something like this, right? It's single pole. So single pole means the slope is going to be minus 20 dB per decade. Okay. We want a gain of 40 dB as our passband gain value. 40 dB gain. Does anyone know what that is in volts per volt? And then we want a anybody? Okay. And then we have a 100. Okay. So that's 100 volts per volt. Thank you, Kent. Okay. And then we have a cutoff frequency of 2 kilohertz. Okay. So the transfer function for a low pass filter, the equations look something like this. Yeah, for a first order, this is a first order, right? Remember, it's single pole, so it's first order. And this is a low pass filter equation. I think in class he has you guys write these equations like this, right? I'm used to this convention, but I think you guys might be more familiar with this. Correct me if I'm wrong. Let's see. So, okay, part A is telling us to find the transfer function given the following circuit. Okay, so let's quickly draw the circuit. So we've got an input, Vn, we have minus and positive terminals like so. We have this capacitor. Can I go back up real quick? Sure. To the way top, is this okay? Do you want to see the graph or were you? That's fine. Okay. Cool. All right. We have this resistor here. We have this resistor like so. Okay. I'm going to try and move a little faster just to save time, guys. We're going to do some other problems. Okay. All right. So it says find the transfer function, right? It doesn't give us anything, and it doesn't, it doesn't say it's ideal, but it also doesn't give us a graph characterizing the output gain or unity gain bandwidth, and it doesn't like say it's not ideal. So we're gonna assume it's ideal. Okay, so we're gonna say VP is equal to VN, and we're gonna say IP is 0 and IN is also 0. Okay, great. That's gonna make this a lot easier to solve. So now we can kind of decouple this circuit. And I'm going to redraw this circuit, and hopefully you guys can follow along with me on how I'm going to drive this. Okay. So I redrew the circuit. So we know how many questions there are. Like with the pace, we're going to be enough for us to finish. I think there's 3 questions on the exam, and you're obviously gonna have to move a lot faster than how I've been going. I'm trying to teach this, so I'm not trying to go too fast, but you do want to feel comfortable during the exam. It's 3 problems, I think, in 50 minutes. I think it's class time, so um, less than 20 minutes per question. So you really want to try and move quickly through each portion of the exam. Now, right away, we're gonna transfer this to the S domain, right? Very simply. So we have these R and C's in parallel. So we have this R2, C2. So I'm just going to quickly call this 1 over SC2. And then we have this 1 over, oh, it looks like they're all SC2s. Okay, nice. And this is R1, this is R1. So I'm going to combine all of these into a single impedance. I'm going to call, in fact, it's going to be identical on both sides, right? Because we have, yeah, we have these two in parallel, and then those are going to be in series. So we're going to call this Z1 and Z1 on top and bottom. So Z1 is just going to be R2 in parallel with 1 over SC2 plus R1. So then our circuit simplifies even further to just become the following. This goes to ground. Start V0, Z1, Z1. Okay. And then our output in terms of our input. Uh, this over this. So yep, yep. There's one final piece, something I'm missing. Okay, that's what I'm missing. So because this portion and this portion of the op amp are equal to each other, I need to keep track of that. So I'm not going to simplify this circuit as much because we can use that to our advantage. So this point on the graph is actually equal to this point on our circuit. Okay. Let's just simplify things a bit more. So instead of this, I'm going to make this a resistor in series with this. Okay. All right. So now we're going to have to use node analysis to solve this. We no longer can kind of breeze through this portion. So taking a look at this node over here, we can say that this point, let's call this X and I'll call this Y. So Vx over Z1. So the new Z1 doesn't have this added on it. So it's going to be something like this. That's the current flowing through. Okay. This will be equal to the current flowing through this branch. And so that's the first Vx, actually. Yeah, Vx is equal to this. And since this whole circuit is in series, I know the current flowing downwards is actually going to be V out minus Vy over Z1 plus R1. And now it's about determining Vx and Vy. So Vn, we need to get Vn in terms of Vx and Vy. Okay. So a couple of things. The voltage drop across Vx, sorry, Vy minus Vn, or sorry, Vy minus Vx, there we go, is going to be equal to Vn subtracted by the voltage drop across the resistors, which um sure I'm looking at this right. Why is Vx not R1, not over R1 plus Z1? Well, yeah, there, yeah, because it's before the node, yeah. So, like Mahi mentioned, Vx is right here. So, yeah. I want to make sure I'm doing this part right. Oh, okay, yeah, I think I like Mahi's equation. Yeah, so Vn minus Vx over R1. So now we have Vn in terms of Vx, and then, but we need to, uh, you said, can't you do it in terms of, can't you do it in terms of all four and set it to zero and then solve for? I'm not understanding. Following the flow of current using the series diagram. So you're saying, okay, so you're saying at this step, the current flowing through this entire branch. Yeah, you can do it all at once. Yeah, I understand your question now. Um, so because this is ground, we can actually define this all at once in terms of the current instead of the voltage. So we can say that, I have to think about this though. Yeah, this is Vn. This is, well, okay, the voltage drop across this is Vn. And this is in the S domain now. And these points are exactly the same. So Vp minus V0 over X1. Oh, I see what you're saying. All the current summing into each of the nodes. Okay. Okay. But you're starting from VP. Okay, okay. I see what you're saying. Yeah. That makes sense. Yes. That's a lot easier. If we do V0 minus VP over Z1 plus the current into this branch, which would be Vn minus Vp over R1. So the current's flowing into this particular node for here. Yep. Plus 0 minus Vp over Z2. The only thing, Mahi, I think you have to be careful is this V in term because mm, because this is a voltage drop between 2 points, it's not directly the voltage at um, this node here. You have to be a bit careful because yeah, it's going to be better to characterize the entire current drop on this portion as the entire um I guess as the voltage across like a larger segment. So I just follow the current path from V0 to ground. Hmm, I think so. Hold on. I don't know why I'm being slow on this one. Let me see. I feel like I'm overthinking this problem. This okay, yeah, I think Mahi, I think you have it. I think you have it. I think I'm understanding what you're saying. I need to think about it a bit more, but for now, we'll. Okay. I you know what? I missed a portion of. Okay, that's what it was. Okay, so there's the second term of the VN. So when I first wrote it, I didn't have the second VN term. Okay, there we go. That this is more clear now. Minus VP over Z2. Okay. All right. So the transfer function is simply the output over the input. So we want to move over the terms, and the problem is this VP term. Here we need to find the VP now in terms of VN. Okay, so the voltage drop for VP, uh, yeah, because we can't move that over. That has to stay there. Yeah, because if we simplify these set of terms, we're gonna get V0 over this. On this side, since we know Z1 and Z2 are equal to each other, this will just be minus 2 VP over Z1. And then these VP terms are actually going to cancel out. So we're going to get this. In fact, I think this whole term is canceling out. Yeah. This whole term just cancels out and we get this. Wouldn't VP be zero? Why would VP be zero? I don't think VP is going to be zero because, right, VP is the voltage at this node. Here. And it's not directly connected to ground. because all we have is VP is equal to VN, and we can come up with a expression for V. And the best way to find like the value of VP is with the nodal analysis, where we can simply say, okay, VP divided by Z1 is going to be equal to VP minus, um, say, VN minus divided by R1. And I think that's going to be the approach we're going to have to take. Um, yeah. And then on the other side, we have this Vn term minus, yeah, yeah, okay. We have this Vn minus V out over Z1 equal to this minus Vn plus all over R1. So you get these two equations, you solve for Vp and Vn on the top and the bottom. So for here, we're going to get Vp over Z1 minus Vp over, say, R1 equal to minus Vn minus over R1, something like this. Vp 1 over Z1 plus 1 over R1. And VP simply becomes, this will be a product over the sum kind of deal. And the R1s are going to cancel out. So we're going to get minus Vn minus times Z1 divided by R1 plus Z1. That's VP. And now we just solve for Vn, and then we set them equal to each other. And that's going to be, and then we'll call Vn is going to be, by the way, Vn is this Vn plus minus Vn minus. By breaking it apart, it becomes a lot easier to solve. Okay, so now for the Vn term, we're going to get this, and I'm going to just Vn, same thing, Z1, R1 plus Z1, the V0 over this. So this becomes V0 R1 over R1 plus Z1 minus Vn plus over R1 plus Z1 times Z1. So Vn is equal to Vp, something like this. And now we set them equal to each other. Vn minus times C1 all over R1 plus C1 is equal to this whole term. Okay. We can move this term over. We get Vn plus minus Vn minus. I factored out the Z1s. We get this R1 plus Z1 term here. And then we get this VO, RO, R1 plus Z1. This just becomes Vn directly. Vn is going to be equal to Z1 R1 plus Z1 equal to V out R1 over R1 plus Z1, and then the output over the inputs simply just becomes Z1 over R1. Wow, that was a very long derivation. Okay. Now Z1 is um this. Okay, so this is just going to be product over sum. And from here, you can just plug in the resistor values, and that would be your transfer function. You can simplify further. I think you guys get the gist from here. So this problem was a bit tricky. So I want to kind of break down like what I did, because dealing with this current source, you have to be a bit careful. We jump over to the S domain when we're handling this particular problem. But what we have is you have this resistor connected with this impedance going to ground, and then you have the same like thing at the top, except it's going to the output. We need to take advantage of the fact that this point right here, which is VP, and this point right here, which is VN, are equal to each other, right? The best way of doing that is by doing nodal analysis at those points. So looking at the current flowing into this point and into this point, and then looking at the current from this point to this point. Else, the problem kind of becomes harder than it needs to be. When you think of it like this, it becomes a lot easier. Also, another thing I did is I broke up the source. Because this source is a differential, it's meaning like this negative sign is not 0 volts. Usually we're used to sources that are connected to ground like this, right? So I can very easily say, okay, if this is 10 volts, right, or whatever, I know I have the AC sign here, but say it's 10 volts, this point up here is 10 volts. But the only reason I can say that is because this here is ground, this is 0, right? So the voltage differential becomes 10 volts. But the moment this becomes some other value other than 0, you no longer know this exact voltage up here. So to simplify it for myself, what you can do when you have a source and it's, one point of it is not connected to ground, um say this is Vn, what I did is I defined a Vn plus term and then call this Vn minus, where Vn is equal to Vn plus subtracted by Vn minus. That way you can take those voltage points directly and use it to solve your problem. So that's what I did to get to this final solution. I think when you do that, it becomes super fast. But you want to get back to this term somehow, this Vn plus minus Vn minus. And I was able to get there. So if this part was confusing, I completely understand. Try working it out on your own, seeing if you get to the same solution I did. You really want to get to this particular um, term right here. But the most important thing is recognizing the VP is equal to VN and doing nodal analysis at those points and setting it equal to each other. So that's what these first equations are right here, right? So this is the VP KCL, this is the VN KCL, right? Now there are other ways of doing this. So if you have, a nice fancy way that gets you to the solution, great. But for folks who might be confused and looking for something that's standard, this is going to be a solid approach, right? Taking advantage that VP is equal to VN, doing nodal analysis, breaking up your source into two distinct points. If it's a differential connection, it's not one point isn't grounded. That's going to be your best bet, and it's going to make this problem a whole lot faster. I wish I could have gotten through more problems. Real talk, with the op-ed problem on the exam be as terrible as this? Maybe. That's I feel like the problems on the exam are involved from what I hear. I don't know what's on the exam. I don't grade exams or anything like that, so I don't know about just from previous sections and previous years. Um, the questions are involved, so do expect them to be like something like this. I'm not gonna lie. You know, I hope the I hope the gain bandwidth product questions like made sense. I hope you guys were able to kind of get a good understanding. Any chance of multiple op amps in one circuit? I did hear one year the instrumentation amplifier was actually on an exam, but that was like some semesters ago, so I'm not too sure. Yeah, I know Mason. I'm sorry. Um, but usually on those ones, I think the analysis is it's like things like one part. I don't think it's super long, but do expect a frequency response question. I hope the frequency response stuff is straightforward. I hope this stuff is. I mean, most everyone kind of focused on the op amps. I know there's one person who asked about frequency response, but hopefully this like drawing the graphs and stuff. Like there's a high chance you get a graphing problem on the exam. I think that's been pretty consistent in the past years. So just keep that in mind. But if there's any additional questions, please feel free to reach out via email. I will be a bit busier. I have another meeting to jump on to like right now. But I will be like up till like probably like 11 or so. So if you guys have like any last minute questions or anything before the exam, feel free to reach out. I hope this was helpful. We spent a long time on that first problem, and um, yeah, there's no other questions. I'm gonna end this meeting. Thank you guys.